Right now, wherever you are, there is probably a computer chip within arm's reach. Maybe it is in the phone on your nightstand. Maybe it is in the laptop you just closed. Maybe it is tucked inside the thermostat on your wall, or the remote on your coffee table, or the little blinking box that gives you Wi-Fi. And inside that chip, there are transistors, tiny switches, billions of them, packed so impossibly close together that the gaps between structures are measured in individual atoms. If you could somehow shrink yourself down and walk among them, you would be standing in a landscape where the laws of physics you learned in school no longer fully apply, where electrons stop behaving like little balls and start behaving like ghosts that can drift through solid walls. And here is the part that really gets me. The raw material for all of this, the foundation of the most sophisticated technology our species has ever created, is sand. Beach sand. Dirt, essentially. The second most common element in the Earth's crust, right after oxygen. Somewhere along the way, we figured out how to take the stuff that gets stuck between your toes at the shore, purify it to an almost unthinkable degree, and arrange its atoms so precisely that a single misplaced particle among billions counts as a catastrophic defect. We learned how to etch structures onto it that are smaller than the wavelength of visible light, which should be physically impossible, and yet we do it millions of times a day, with a reliability that would make a Swiss watchmaker quit in admiration. How did we get here? The journey from the first crude electronic switch to the chip in your phone involved overcoming obstacles that seemed physically impossible at the time. It involved feuds between brilliant people that destroyed friendships and created empires. It involved a single company in a small Dutch town that no one has heard of, building a machine that costs more than a Boeing 787, and without which no advanced chip on Earth can be manufactured. It involved vaporizing 50,000 droplets of molten tin per second with a laser to create a miniature star inside a vacuum chamber. It involved polishing mirrors to a smoothness where, if you scaled them up to the size of a country, the tallest bump would be shorter than a millimeter. It involved sand. That is what I want to talk about tonight, the whole story from the very beginning. And I want to take my time with it, because this story deserves to be told slowly. Because the real history of the computer chip is not a smooth, triumphant march of progress. It is a story about walls, about hitting limits that seemed absolute. Barriers that serious people with serious credentials said could never be crossed. And then somehow, stubbornly, brilliantly, sometimes accidentally, finding a way through. Over and over and over again. And every time we broke through one wall, we ran headlong into the next one. And each new wall was harder than the last. The materials were stranger. The physics was meaner. The engineering tolerances were tighter. The price tag was bigger. And the number of people who truly understood the whole picture got smaller and smaller. Until today, when the device in your pocket contains more components than there are people on Earth, and no single human being alive fully understands every part of how it works. So here are the questions I want us to sit with tonight. How did we go from a machine that weighed 30 tons and filled an entire room to a chip the size of your fingernail that is millions of times more powerful? What walls did we hit along the way, and how did we break through them? Why did the people who made the biggest breakthroughs so often end up destroying the very teams that made them possible? And what happens when we finally hit a wall we cannot break? Because here is the thing that most people do not realize. The supply chain that puts a working chip into your phone stretches across a dozen countries, depends on machines that only one company on Earth knows how to build, and runs through factories sitting in some of the most geopolitically fragile places on the planet. If that chain breaks, it does not just affect tech companies. It affects your car, your hospital, your bank, your power grid, your ability to heat your home or call for help. The chip in your pocket is the product of the most complex and most fragile manufacturing system humanity has ever built. And almost nobody thinks about it until it stops working. If you drift off somewhere along the way, that is perfectly fine. The story will still be here. Let us start at the beginning. To understand the story of the computer chip, you first need to understand a simple problem. How do you control electricity? Not just generate it or send it down a wire. Control it. Make it do what you want. Make it stop when you want it to stop. Make it carry information, make decisions, perform calculations. Because electricity on its own is just a flow of charge. It does not think. It does not compute. It just moves, the way water moves through a pipe. To make it useful, you need a way to turn it on and off, very quickly, very reliably, and ideally very cheaply. You need a switch. Now, the first really useful electrical switch was invented in the early years of the 20th century, and it looked nothing like what you might imagine. It was a glass bulb with the air pumped out, a small metal plate suspended inside, and a heated wire filament at the bottom that glowed when you ran current through it. It was called a vacuum tube, and it worked on a principle that seems almost charmingly simple when you describe it. Here is what happens inside. When you heat a wire filament hot enough, the metal starts shedding electrons. They just boil off the surface the way steam rises from a pot of water. Those electrons are negatively charged, so if you put a positively charged metal plate nearby, the electrons will fly toward it, because opposite charges attract. And just like that, you have a current flowing through the vacuum inside the tube, from the filament to the plate. If the plate is positive, current flows. If the plate is negative or neutral, the electrons get repelled and current stops. You have a switch. On or off, 1 or 0. But the really clever part came in 1907, when an American inventor named Lee DeForest figured out that if you placed a small grid of wire between the filament and the plate, you could use a tiny electrical signal on that grid to control a much larger current flowing through the tube. A small nudge on the grid caused a big change in the flow. The tube could amplify. It could take a faint signal, a weak radio wave picked up by an antenna, a whisper of a telephone call fading across hundreds of miles of wire, and make it louder, stronger, big enough to hear. This was the technology that made radio possible. It made long-distance telephone calls possible. It made the first televisions possible, and radar, which helped win the Second World War. For half a century, vacuum tubes were the beating heart of electronic technology. But vacuum tubes had problems, and those problems turned out to be a wall. They were big. Each tube was roughly the size of your thumb, sometimes bigger. They ran incredibly hot, because that filament had to glow white hot to shed electrons, just like a light bulb. In fact, a vacuum tube was essentially a specialized light bulb, and like a light bulb, it burned out. Constantly. The filaments degraded, the glass cracked, and the tubes failed at unpredictable intervals, sometimes after thousands of hours, sometimes after a few hundred, sometimes after a few days. And they consumed enormous amounts of power. Each tube was a tiny furnace, and if you needed thousands of them working together, the heat and the power draw became serious engineering problems in their own right. Now, if all you needed was a radio or a telephone amplifier, a handful of tubes worked just fine. The radio in your living room might use 5 or 6 of them. A radar set might use a few dozen. But what if you wanted to build something more ambitious? What if you wanted to build a machine that could calculate? The military had a problem during the war, and it was a problem of speed. They needed to compute firing tables for artillery, long lists of numbers that told gunners exactly how to aim their cannons under different conditions, different distances, different wind speeds, different elevations, different temperatures. Each table required thousands of calculations. Computing them by hand, using teams of mathematicians working with desk calculators, took weeks or months. By the time a table was finished, the tactical situation might have changed entirely. The military wanted a machine that could do it faster. Two engineers at the University of Pennsylvania, John Mauchly and J. Presper Eckert, proposed building an electronic calculator that could do in seconds what human mathematicians took days to accomplish. The military funded the project, and by 1945, the machine was ready.
The result was ENIAC, the Electronic Numerical Integrator and Computer. And ENIAC was a marvel. It could perform 5,000 additions per second, roughly 1,000 times faster than any mechanical or electromechanical computer in existence. Press articles described it with a mix of awe and bewilderment, struggling to convey the scale of what had been built. The United States Army was so proud of it that they featured it in recruitment advertisements. When it was demonstrated to the public, people lined up to see it, though what they saw was less a sleek machine than an overwhelming wall of metal, glass, and blinking lights. Mauchly and Eckert, along with the mathematician John von Neumann, went on to propose a successor called EDVAC that introduced the revolutionary idea of storing programs alongside data in the same memory, rather than having to rewire the machine for each new calculation. This concept, the stored program architecture, sometimes called the von Neumann architecture, became the blueprint for virtually every computer that followed. Every laptop, phone, and server you have ever used runs on a descendant of that idea. But ENIAC was also a monster. It used nearly 18,000 vacuum tubes. It weighed about 30 tons. It filled an entire room, a big room, roughly 30 feet by 50 feet, and it consumed around 150 kilowatts of power, enough to run dozens of homes. There is a story, and the specifics are debated, but the spirit is absolutely true, that when ENIAC was running at full power, the lights in the surrounding neighborhood would dim. The machine was literally pulling so much electricity that there was less left for everyone else. And those 18,000 tubes failed constantly. Some estimates suggest that a tube blew roughly every other day. Each time one died, the entire machine had to be shut down, and technicians had to crawl through the guts of this enormous apparatus, testing tube after tube, hunting for the dead one, replacing it, and then firing the whole system back up again. A significant fraction of the time that ENIAC was operational was spent just finding and replacing burned-out tubes. People could see where this was heading, and it was nowhere good. If you wanted a more powerful computer, you needed more tubes. More tubes meant more heat, more power, more failures, more cost, and a bigger room to put it all in. You could not just scale up. A computer with 100,000 tubes would be the size of a building, would need its own power plant, and would probably never run long enough between failures to finish a calculation. The vacuum tube was a brilliant invention, but it had a ceiling, a hard physical limit on how far it could take you. The first wall. And the people who understood computing best knew they were pressed right up against it. What they needed was something that could do exactly what a vacuum tube did: switch an electrical current on and off, amplify a signal, act as a controllable gate for the flow of electrons. But it had to be smaller, it had to be cooler, it had to use less power, and it had to last longer than a light bulb. And the answer, it turned out, was hiding in a material that almost nobody thought was interesting. A material that was neither a good conductor nor a good insulator, but something strange and in between, a material that came from one of the most common substances on the planet: sand. To understand what happened next, you need to understand one small but crucial piece of physics. Just one. And I promise it is simpler than it sounds. Materials in the world come in roughly 3 types when it comes to electricity.
There are conductors, like copper and gold, where electrons move freely and electricity flows easily, like water through an open pipe. There are insulators, like rubber and glass, where electrons are locked in place and electricity cannot flow at all, like water hitting a sealed wall. And then there is this strange third category, this wonderfully weird in-between zone called semiconductors. A semiconductor is a material where electricity sort of flows. Under normal conditions, it is a lousy conductor. The electrons are mostly stuck. But if you nudge the material in the right way, if you heat it up or shine light on it, or add tiny amounts of certain impurities, you can free up some of those electrons and make them move. You can push a semiconductor from being almost an insulator to being almost a conductor, and back again. You can control the switch. Silicon is a semiconductor, and silicon is everywhere. It is the second most abundant element in the Earth's crust, after oxygen. It is the primary ingredient in sand, in rocks, in glass. The stuff beneath your feet, the stuff that gets between your toes at the beach, the stuff that ancient people used to make arrowheads and pottery, contains the element that would eventually power every computer, every phone, every digital device on the planet. But that was not obvious to anyone in the 1940s. Silicon and its cousin germanium were curiosities, interesting to physicists, useful for a few niche applications, but not the kind of thing that was going to change the world, or so people thought. The place where the breakthrough happened, the specific physical location, was Bell Telephone Laboratories in Murray Hill, New Jersey. And Bell Labs in the 1940s was one of the most extraordinary concentrations of scientific talent the world has ever seen. It was the research arm of AT&T, the American telephone monopoly. And because AT&T was so enormously profitable, because it controlled virtually all long-distance telephone service in the country, it could afford to do something remarkable. It could pay very smart people to work on very hard problems without demanding immediate commercial results. The culture at Bell Labs was unusual, and it is worth spending a moment on, because the environment mattered as much as the individuals. The labs had just moved from a cramped facility in Manhattan to a new campus in the hills of New Jersey, a sprawling, modern building designed to promote exactly the kind of accidental collaboration that leads to breakthroughs. The hallways were deliberately long, so that people from different departments would bump into each other on the way to the cafeteria. Physicists worked alongside chemists, who worked alongside metallurgists, who worked alongside engineers. There were no rigid hierarchies of the kind you found at universities or most corporations. If you had an idea, you could walk down the hall and find someone who could help you test it, usually before lunch. The social atmosphere was informal and creative. There were parties, picnics, and an annual musical review, where scientists wrote and performed songs about their research, with titles like Lab Hell. Walter Bratton's lab notebook from this period radiates enthusiasm. He wrote that he could not exaggerate the extraordinary working relationship of the group, that they met freely to discuss important topics at any time, that ideas flowed without bureaucratic barriers. This environment
was not accidental. The director of research, a man named Mervyn Kelly, had spent years thinking about how to organize scientists for maximum creativity. Kelly understood that the biggest breakthroughs happened at the boundaries between disciplines, where a physicist's insight collided with a chemist's technique, or a metallurgist's materials knowledge. He designed Bell Labs to maximize those collisions. The labs had already produced a Nobel Prize and were generating patents at a pace of roughly 2 per day. It was, by any measure, one of the most productive research organizations in human history. And the conditions that made it work, the freedom, the funding, the mixing of disciplines, the tolerance for failure, serve as a reminder that great inventions do not happen in a vacuum. They happen in environments that are carefully designed to make them possible. AT&T had a specific problem it wanted solved. The telephone network depended on vacuum tubes to amplify signals across long distances, and those tubes were becoming a bottleneck.
They burned out, they ran hot, they were expensive to maintain, and if the demand for telephone calls kept growing the way it was growing, half the women in America would need to be employed as telephone operators, as one executive jokingly but nervously observed. AT&T needed something better than vacuum tubes, and the man put in charge of finding that something was a physicist named William Shockley. Shockley was brilliant. There is no question about that. He had a deep physical intuition, a gift for seeing how electrons move through materials almost as if he could watch them. A colleague once said that Shockley could see the electrons, and while that was obviously a figure of speech, it captured something real about the way his mind worked. He understood semiconductor physics at a level that very few people in the world matched. But Shockley was also ambitious in a way that burned. He wanted credit. He wanted to be first. He wanted his name on the breakthrough, and that desire, which drove him to brilliance, would also eventually drive him to behavior that destroyed the best team he ever assembled. Shockley had been thinking about semiconductor amplifiers since before the war. His idea was that you could use an electric field to control the flow of current through a slab of semiconductor. Apply a charge to the surface, and the field would reach into the material, pull electrons around, and open or close the flow, just like the grid in a vacuum tube controlled the electron stream from filament to plate. The theory was elegant. It should have worked. It did not work. They built the device. They tested it. Nothing happened. The semiconductor sat there stubbornly refusing to amplify anything. The math said yes. The material said no. Shockley knew he could not do it alone. He was a brilliant theorist, but he was terrible at experimental work, terrible with his hands. He needed someone who could translate ideas into physical devices, someone who could build things in the lab and make them work. And he needed someone who could figure out, at a deep theoretical level, why his amplifier design was failing, because the failure was genuinely mysterious. The math said it should work. The semiconductor should have responded to the electric field, but it was stubbornly silent. This is where two other people enter the story, and they matter enormously. John Bardeen was a theoretical physicist, quiet and unassuming, the kind of person who could sit in a room full of louder, more confident people and say almost nothing for an hour, and then offer a single observation that reframed everything. He was brilliant in a way that was easy to underestimate because he never raised his voice and never seemed to need anyone to know how smart he was. His colleagues called him Whispering John. He would eventually win 2 Nobel Prizes in physics, which is a club with very, very few members. Walter Brattain was an experimental physicist, a hands-on tinkerer, a man who loved building things and making them work. He grew up on a ranch in the state of Washington and had a practical, almost agricultural ingenuity about him.
If you needed a piece of lab equipment and it did not exist, Bratton could build it out of wax, wire, and whatever else was lying around. He was the kind of person who could make anything work, at least once. Shockley assigned Bardeen and Bratton to figure out why his field effect idea was failing. And what Bardeen eventually figured out, after months of careful thought, was that the problem was on the surface of the semiconductor. Electrons were getting trapped there, forming a kind of invisible shield, and that shield was blocking the external electric field from penetrating into the material.
The field could not reach the electrons inside because the electrons on the surface were screening it out. This could have been the end of the story. Surface states were a problem, and problems without solutions are just walls. But Bardeen and Bratton did not stop. With Shockley stepping back to work on his own projects, the two men had the freedom to explore on their own terms, and they used that freedom brilliantly. They tried everything they could think of. They submerged semiconductor samples in various electrolytes, reasoning that the charged particles in a liquid might neutralize the surface barrier. They tried different materials. They tried germanium instead of silicon and found it more cooperative. They dunked germanium in water and noticed a faint response, enough to confirm Bardeen's theory about the surface states, but not enough to be useful. The liquid seemed to slow things down, making the response too sluggish to amplify the frequencies of a human voice, which was what AT and T cared about most. Then Bratton, ever the improviser, tried something new. Instead of a liquid, he placed a thin oxide layer between a metal contact and the germanium surface. And in one experiment, he accidentally washed the oxide away, leaving the metal in direct contact with the semiconductor. Instead of the field effect they had been pursuing, what they observed was something different entirely. Charge carriers were being injected directly into the material. It was a completely different mechanism from what they had expected, and it worked far better. And then, on December 16, 1947, Walter Bratton rigged up one of the most delicate and improbable contraptions in the history of technology. He took a small triangle of plastic, wrapped a strip of gold foil around it, and slipped the foil down the middle with a razor blade to create two contact points, incredibly close together, just a hair's breadth apart. Then he pressed both points gently down onto a tiny slab of germanium. When they applied a small signal to one gold contact, they got a larger signal out of the other. It amplified. It actually worked. This was the first transistor. They called it the point contact transistor, and honestly it was a fragile, finicky, temperamental device. It looked like something you might break by sneezing near it. But it worked. It could do what a vacuum tube did, and it was tiny, and it barely used any power, and it did not burn out. The first wall had been broken. But now comes the human drama, and this part matters because it shaped everything that followed. William Shockley was not in the room when Bardeen and Brattain made their breakthrough. He was not part of the experiment. His name was not on the patent, and according to people who knew him, this ate at him in a way that fundamentally changed who he was. Shockley was the one who had started this entire line of research. He was the one who had the original vision, who had been dreaming of a semiconductor amplifier for years. And now his subordinates had done it without him, and they were going to get the credit, and his name was nowhere on the invention. So Shockley did something remarkable, and depending on how you look at it, either heroic or ruthless. Over the Christmas holiday of 1947, just days after Bardeen and Bratton's demonstration, Shockley went off on his own. He checked into his hotel room during a physics conference in Chicago, and while everyone else celebrated New Year's Eve,
He sat alone, filling notebook page after notebook page with calculations and ideas, working with an intensity that bordered on obsession. And he came up with a different design, a better design. Instead of those delicate point contacts pressing onto a surface, Shockley envisioned a sandwich of semiconductor layers with different electrical properties stacked together. An emitter layer, a base layer, and a collector layer. Apply a small signal to the base, and you control a much larger current flowing from emitter to collector. He called it the junction transistor. The junction transistor was more robust than Bardeen and Brataine's point contact device. It was more reproducible, it was easier to manufacture, and it pointed the way toward how transistors would actually be built at scale for decades to come. When transistor radios appeared in the 1950s, when computers started replacing their vacuum tubes with solid-state components, it was Shockley's junction design they used, not the original point contact transistor. But Shockley did something else during this period that poisoned the well. He kept his work secret. He did not tell Bardeen or Brattain what he was doing. He worked behind their backs. And when he revealed his junction transistor, the message was unmistakable. I am the one who matters here. Your invention was just a stepping stone to mine. He also tried to get his name added to Bardeen and Brattain's patent, arguing that their work was fundamentally derived from his original ideas. The patent lawyers at Bell Labs, to their credit, looked at the facts and said, no. Shockley had contributed to the broader research program, but the point contact transistor was Bardeen and Brattain's invention, and their names alone belonged on that patent. The relationship between the three men never recovered. In 1956, Shockley, Bardeen, and Brattain shared the Nobel Prize in Physics for the invention of the transistor. The Swedish Academy described their work as a supreme effort of inventive vision and perseverance, exercised individually and as a team. But by the time they stood together in Stockholm, they could barely stand each other. Bardeen left Bell Labs. He went to the University of Illinois, where he would eventually win his second Nobel Prize for completely different work on superconductivity. Brattain was gradually sidelined, and Shockley, consumed by ambition and the conviction that he deserved more credit than anyone else, left too. He headed west to California, to a quiet town called Palo Alto, near Stanford University. He started a company, Shockley Semiconductor Laboratory. He recruited some of the best young minds in the field, luring them with his fame, his Nobel Prize, and the promise of working at the frontier of technology. Among the people he hired were two young physicists named Robert Noyce and Gordon Moore. But Shockley's brilliance at recruiting was matched only by his dysfunction as a manager. He was paranoid, controlling, and erratic. He insisted that everyone work on the projects he cared about, in the way he wanted them worked on, and he reacted badly to disagreement. When he decided the company should pursue a particular type of four-layer diode that he found theoretically interesting, his engineers tried to tell him the market did not want it. He did not listen. Within 18 months, 8 of his best engineers quit. They walked out together. In Silicon Valley law, they are known as the traitorous 8, and the name says everything about how Shockley felt about their departure. He considered it a personal betrayal, an act of disloyalty that he never forgave. Those 8 engineers founded a new company called Fairchild Semiconductor, and the things they built there would change the world in ways that Shockley's company never did. Shockley's company, meanwhile, withered. He spent the rest of his career at Stanford, growing increasingly isolated. In the 1970s and 80s, he became notorious for promoting discredited theories about intelligence and genetics, views that alienated virtually everyone who had ever respected him. When he died in 1989, his children learned about it from the newspaper. They had been estranged for years. The man who could see the electrons, who had the original vision that led to the transistor, who arguably understood semiconductor physics better than anyone alive, ended up alone. His brilliance built the foundation of the digital age, and his character ensured he would have no part in what came after. But the transistor itself was thriving, even as the men who invented it drifted apart. By the mid-1950s, transistors were showing up everywhere, and the first place most ordinary people encountered them was in their hands. The transistor radio changed the world in ways that are easy to underestimate now. Before transistor radios, if you wanted to listen to music or news, you sat in your living room next to a piece of furniture. Vacuum tube radios were large, heavy, fragile, and plugged into the wall. You did not take them anywhere. Music was something that happened in specific places. The transistor radio changed that. In 1954, a company called Regency, in partnership with Texas Instruments, released the TR-1, the first commercial transistor radio. It fit in a shirt pocket. It ran on a small battery. It cost about $50, which was 3 times the price of a tube radio. But it was portable, and that portability was worth everything. It sold out immediately. Other manufacturers followed, but American companies quickly realized that the military market was far more profitable. Why make a few dollars selling a pocket radio when the Pentagon would pay $100 or more for a single transistor? So American companies largely abandoned consumer transistor products and focused on defense contracts. That left the consumer market wide open. 2 Japanese engineers, Masaru Ibuka and Akio Morita, saw the opportunity. They ran a small company that had been making tape recorders in a bombed-out warehouse in Tokyo. When they learned that Bell Labs was licensing the transistor patent, they immediately understood its potential for making radios. They licensed the technology, mastered the manufacturing, and gave their company a name that would be easy to pronounce in any language: Sony. Sony and other Japanese manufacturers flooded the world with transistor radios, and those radios did something profound. They put information into the hands of people who had never had it before. A shepherd in the Sahara could hear news from Cairo. A teenager in her bedroom could listen to music her parents had never heard of, music that was getting louder, bolder, more rebellious, because the audience was no longer sitting in a living room under parental supervision. The transistor radio was arguably the first personal electronic device, and it reshaped culture in ways that are still echoing. Meanwhile, Shockley's company was disintegrating. The traitorous 8, the engineers who had walked out on him, founded Fairchild Semiconductor with backing from Sherman Fairchild, a wealthy industrialist and inventor. And Fairchild Semiconductor became one of the most important companies in the history of technology, not only for what it built, but for what it spawned. The culture at Fairchild was the opposite of Shockley's paranoid autocracy. Robert Noyce, who led the group, was collaborative and egalitarian. There were no reserved parking spaces. Titles meant little. If you had a good idea, you could pursue it. The company attracted brilliant engineers and then let them run. And the result was a burst of innovation that laid the groundwork for everything that came after. It was at Fairchild that the planar process was perfected, the technique of building transistors on a flat surface, using photographic methods and oxide layers, which made mass production possible. It was at Fairchild that Jean Herney developed the planar transistor, with its protective oxide layer that made devices far more reliable. And it was at Fairchild that Robert Noyce conceived the planar integrated circuit. But Fairchild Semiconductor had its own problems. The parent company, Fairchild Camera and Instrument, siphoned profits from the semiconductor division to prop up its other, less successful businesses. The engineers who were generating billions felt they were not sharing in the rewards. And one by one, they started leaving to found their own companies. The exodus from Fairchild seeded an entire ecosystem, and it followed a pattern that was starting to look like a law of nature in the semiconductor industry. Shockley's obsessive need for control drove away the people who could have made him great. And now Fairchild was doing the same thing, just differently. The parent company treated its semiconductor division like a cash cow, milking the profits while starving the engineers of the rewards and autonomy they craved. So the engineers left, one by one, then in waves. Jerry Sanders left to found AMD. Charlie Spork went to National Semiconductor. Other alumni founded dozens of companies up and down the peninsula south of San Francisco. The region, once known for its orchards and apricot farms, began filling up with semiconductor startups.
People started calling it Silicon Valley, and the name stuck, because the valley was quite literally built on silicon, manufactured by companies founded by people who had learned their trade at Fairchild, which itself was founded by people who had fled from Shockley, who had gotten the whole thing started by bringing brilliant people to California in the first place. The pattern would keep repeating. Federico Faggin, the Italian engineer who would soon design the world's first commercial microprocessor at Intel, would eventually leave Intel after feeling his contributions had been overlooked, and go on to found Zilog, a direct competitor. Years later, key architects of AMD's resurgence would be engineers who had walked away from Intel. The semiconductor industry was built over and over by people leaving one organization and starting another, driven by the same volatile mix of ambition, frustration, and creative hunger that had propelled the traitorous eight out of Shockley's lab. The breakthroughs came not from harmony, but from fracture. Every rupture released energy that went into building something new. Shockley never benefited from any of it. His company never produced a commercially significant product. The man who could see the electrons, whose vision and stubbornness had set the entire industry in motion, watched from the sidelines as his former employees built empires on the foundations he had laid. If he had been a better manager, if he had shared credit, if he had listened, he might have been the richest person in the world. Instead, he is remembered as the father of Silicon Valley in a cautionary sense, the brilliant man who drove away everyone who could have made his dreams real. And yet, even as the transistor revolution was transforming consumer electronics and computing, the next wall was already visible. Because having a transistor is not the same thing as having a computer chip, not even close. A single transistor is just a switch to do anything useful, to perform calculations, to store data, to run a program. You need thousands of them, tens of thousands, connected together in specific patterns to form circuits. And connecting them was becoming a nightmare. Here is the problem that the world faced in the late 1950s. And it is worth slowing down to really understand it, because the solution to this problem is what gave us the modern world. You could make a transistor. That part was solved. By the mid-50s, factories were churning out individual transistors by the millions, each one a tiny component packaged in a little metal can with wire leads sticking out of it, ready to be soldered onto a circuit board, alongside resistors and capacitors, and all the other components a circuit needs. But making the circuit, wiring all those components together, was still done essentially by hand. A technician would solder each connection, one at a time, linking transistor to resistor to capacitor, wire by wire. Each solder joint was a potential point of failure. Each wire was something that could come loose, corrode, or break.
And as circuits got more complex, the number of connections grew faster than anyone could manage. The military wanted more sophisticated electronics for missile guidance systems and aircraft. The telephone company wanted better switching equipment. Computers were getting more capable, which meant they needed more transistors, which meant more connections, which meant more potential failures and more cost. Engineers had a name for this problem, and it was a good one: the tyranny of numbers. You could design a circuit on paper that needed 10,000 transistors, and the design would be elegant and powerful. But actually building it, actually wiring those 10,000 components together without a single error, was becoming the bottleneck.
The transistor itself had been miniaturized, but the way circuits were assembled had not kept pace. Individual components kept getting smaller, but the spaces between them, the wires connecting them, the solder joints holding everything together, those were stubbornly, irreducibly large, and every connection was a liability. Think about it this way. If each solder joint has a 99.9% chance of being reliable, which sounds very good, and you have 10,000 of them, the probability that all of them work is only about 90,005%. You have roughly a 1 in 10 chance that at least one connection has failed somewhere in your circuit. Scale that up to 100,000 connections, and the math becomes hopeless. You are virtually guaranteed to have failures, and finding a single bad connection among 100,000 is like finding a single burned-out bulb in a string of Christmas lights that stretches from New York to Chicago.
That was the wall. You could make the parts, but you could not assemble them fast enough, cheaply enough, or reliably enough to build the things that people wanted to build. The transistor had shattered the vacuum tube barrier, but the tyranny of numbers was an entirely different kind of obstacle, and there was no obvious way around it. Unless you change the question entirely. What if, instead of making each component separately and then wiring them all together, you could make everything at once? All of it. The transistors, the resistors, the capacitors, the connections between them. All out of the same piece of material. All in one process. What if the entire circuit could be built on a single chip? Two people, working independently on opposite sides of the country, arrived at this idea at almost exactly the same time. And the way it happened tells you something important about how breakthroughs work. They do not usually come from a single mind in isolation. They come when the problem is ripe, when the tools are ready, when the pressure is intense enough that multiple smart people start converging on the same solution from different directions. The first was Jack Kilby. Kilby was a tall, quiet, slightly awkward electrical engineer from Kansas. He had been working at a company called Centralab in Milwaukee, making hearing aids and small electronic assemblies, and in the spring of 1958, he took a job at Texas Instruments in Dallas. He was new there, brand new, and when the company shut down for a mandatory 2-week vacation in July, Kilby did not have any vacation days accrued. So while almost everyone else was gone, he was alone in the lab. He spent those 2 empty weeks thinking, mostly alone, in a quiet building with the air conditioning turned down and the hallways empty. No meetings, no interruptions. Just Kilby and a notebook and the tyranny of numbers. And the idea he arrived at was, in retrospect, almost obvious, which is how you know it was a truly great idea. Because the best ideas always seem obvious after someone has them. The sign of a genuinely revolutionary insight is that once you hear it, You cannot imagine thinking any other way. And yet, before someone said it out loud, nobody did. What if you could make all the components, transistors, resistors, capacitors, out of the same block of semiconductor material? You would not need to wire separate parts together. The circuit would be monolithic. One stone, one piece, everything integrated. On September 12, 1958, Kilby demonstrated a working integrated circuit built on a single piece of germanium. The components were connected by tiny gold wires that had been bonded by hand under a microscope, and the whole thing looked, frankly, like a mess. It was an oscillator, a circuit that produces a repeating signal. When Kilby connected it to an oscilloscope and switched it on, a clean sine wave traced across the screen. His boss looked at it and reportedly said 2 words. "That is it." And it was. That was the first integrated circuit. But it was rough, hand-assembled, fragile, and very hard to imagine manufacturing at scale. The gold wires connecting the components were bonded one at a time, and if you needed a more complex circuit with more connections, the whole thing became impossibly fiddly. Halfway across the country, someone else was working on the same problem, and his solution was, in some ways, even more important. Robert Noyce was one of the traitorous 8, one of the brilliant young engineers who had walked out of Shockley's lab to found Fairchild Semiconductor. Noyce was charismatic, confident, and had a mind that combined deep technical insight with an almost casual willingness to take risks. He was the kind of person who made hard problems seem simple, partly because he was very smart, and partly because he genuinely did not seem to worry much about failure. And Noyce's solution to the tyranny of numbers had a crucial difference from Kilby's. Instead of connecting components with hand-bonded wires, Noyce figured out how to use the same photographic techniques that were already being used to pattern transistors on silicon to also create the metal connections between them. You could print the entire circuit, transistors and wiring and everything, layer by layer, onto a flat piece of silicon using light and chemistry. No hand wiring, no individual assembly. The entire thing could be fabricated as a single, monolithic piece. This was the real revolution. Kilby proved the concept that you could put an entire circuit on a single chip. But Noyce showed how to manufacture it, and manufacturing was what turned a laboratory curiosity into a world-changing technology.
Noyce filed his patent in July of 1959. What followed was a long, complicated patent dispute between Texas Instruments and Fairchild Semiconductor, with both companies claiming priority. The dispute was eventually resolved with both Kilby and Noyce being recognized as co-inventors of the integrated circuit. Both of them earned the title Father of the Microchip, and it was Noyce's planar process, the technique of building circuits layer by layer using photographic methods, that became the blueprint for the entire semiconductor industry. Now, I want to pause here and make an observation about what had just changed, because the shift was more profound than it might seem at first. With Kilby and Noyce's integrated circuit, the fundamental unit of electronics was no longer the individual component. A transistor was no longer a thing you bought from a supplier, soldered onto a board, and connected with wires. Instead, transistors and resistors and capacitors were all features, patterns printed onto a surface, like letters on a page. And just as a printing press does not care whether the page has 10 words or 10,000, the process of building an integrated circuit did not fundamentally change depending on how many components you put on the chip. More transistors did not mean more assembly.
They just meant a more detailed pattern on the mask. This was the insight that broke the tyranny of numbers. The tyranny existed because assembly was the bottleneck, because each connection was an individual act of human labor. The integrated circuit eliminated assembly. Everything was printed at once. The number of components on a chip could grow without the cost growing in proportion. And that meant the question was no longer, can we build circuits with thousands of transistors? The question was now, how many transistors can we print on a single chip?
The first integrated circuits in the early 1960s had a handful of components, maybe a dozen transistors. They were impressive, but not exactly world-shaking. But people started noticing something. Every year, the number of transistors engineers could fit onto a single chip was roughly doubling. The features got smaller, the processes got more refined, and the yield improved, meaning a higher percentage of chips came out working. The person who first noticed this pattern and wrote it down was Gordon Moore, the other half of the pair that had left Shockley's lab with Noyce. Moore was a chemist by training, quiet and analytical, nothing like the flashy Noyce. In 1965, he wrote a paper for Electronics magazine in which he plotted the number of components on the most cost-effective chips over the previous few years, noticed the remarkably consistent doubling trend, and predicted it would continue for at least another decade. That prediction became known as Moore's Law, and it turned out to be one of the most consequential observations in the history of technology. Now, Moore's Law is not a law of physics. Gravity is a law of physics. Thermodynamics is a law of physics. Moore's Law is not like that. It is an observation about engineering progress, a trend, a pattern that Moore noticed and expected to continue. Around 1975, he revised the doubling period to roughly every 2 years, and that is the version most people know. The number of transistors on a chip roughly doubles every 2 years. And here is the wild part. It held. For decade after decade after decade. Not because the universe required it, but because the semiconductor industry organized itself around making it happen. Companies planned their research roadmaps years in advance based on where Moore's Law said they should be. Customers expected the next generation of chips to be faster and denser. Competitors raced to keep pace.
The industry literally created formal documents, technology roadmaps, that laid out the schedule. By this year, we need features this small. And by this later year, features that small. And here is what we need to invent to get there. Moore's Law became the metronome that the entire industry marched to. It was a self-fulfilling prophecy in the best possible way. A single graph with a handful of data points, drawn by a quiet chemist in 1965, shaped the trajectory of human civilization for the next 60 years. But making transistors smaller was not just a matter of wanting it badly enough. At every step, there were real, physical, often terrifying obstacles. The walls kept coming. And before we get to the next great wall, we need to talk about what happened when you could finally put enough transistors on a chip to build something truly transformative. A complete computer on a single piece of silicon.
For the first decade or so of integrated circuits, from the early 60s to the early 70s, chips were getting more complex, but they were still performing relatively simple functions. A chip might contain a few hundred or a few thousand transistors, enough to implement a logic gate, a memory register, a simple amplifier. You still needed many different chips, wired together on a circuit board, to build anything resembling a computer. The integrated circuit had solved the tyranny of numbers at the component level, but building a full system still required assembling boards full of separate chips. The question that several people started asking in the late 1960s was whether you could put an entire processor, the central brain of a computer, on a single chip. The answer came from a somewhat unlikely direction.
In 1969, a Japanese calculator company called Busicom approached Intel, a young semiconductor company that mostly made memory chips, and asked them to produce a set of custom chips for a new line of programmable calculators. The original design called for 7 separate chips. An Intel engineer named Ted Hoff looked at the design and proposed something radical. Instead of building 7 specialized chips that could only run calculators, why not build one general-purpose processor chip that could be programmed to do different things? You would need fewer chips, which would lower costs, and the same chip could potentially be used in other products. Hoff sketched out the concept, but he was not a chip designer and moved on to other projects. The task of actually designing and building the chip fell to an Italian engineer named Federico Fagin, whom Intel had recently hired from Fairchild Semiconductor.
At Fairchild, Fagin had invented a crucial transistor technology called the self-aligned gate, which allowed transistors to be made smaller and faster. Fairchild had been reluctant to adopt the technology, so when Fagin moved to Intel, he put it to work immediately. The result was the Intel 4004, delivered to Busicom in 1971. It had 2,300 transistors, ran at a clock speed of 740 kHz, and could process 4 bits of data at a time. By modern standards, it was laughably primitive, but it was a complete central processing unit on a single chip, a computer brain the size of a fingernail. Busicom sold over 100,000 calculators powered by the 4004, and the microprocessor era had begun. The next step was the Intel 8008, the first 8-bit microprocessor, which could handle data in chunks twice as large.
The 8008 was soon replaced by the 8080, a much faster and more capable chip, and that chip caught the attention of a calculator manufacturer called MITS. Ed Roberts, the founder of MITS, realized that the 8080 was powerful enough to build a simple home computer around it. But the chip cost $350 per unit, which was too expensive for a consumer product. As one of Intel's largest customers, Roberts negotiated the price down to $75, and with that, he built the Altair 8800, generally considered the first commercially successful personal computer. The Altair was crude. It had no keyboard, no screen, and no permanent storage. You programmed it by flipping switches on the front panel, 1 bit at a time. But it was a real computer that an individual could own for a few $100s, and it ignited the imaginations of an entire generation of engineers and hobbyists who had learned programming in college but had no hardware of their own to play with. Meanwhile, other chips appeared. The Motorola 6800 was released just 4 months after the 8080, but poor management decisions at Motorola drove most of the 6800's design team to walk out, led by engineers Chuck Peddle and Bill Mensch. They joined a small company called MOS Technology and designed a simpler, cheaper processor by stripping out unnecessary features, trimming the instruction set, and dramatically improving the manufacturing process to reduce defect rates. The result was the MOS Technology 6502, which debuted at a trade show in San Francisco in 1975 with a price tag of $25. The Intel 8080 cost $350.
The Motorola 6800 cost $175. The 6502 cost $25. Demand was immediate and overwhelming. Motorola sued MOS Technology for patent infringement. MOS settled and was eventually acquired by Commodore, but the 6502 had already changed the landscape. It powered the Apple II, the Commodore 64, the Atari 2600, the BBC Micro, and the Nintendo Entertainment System. An entire generation of home computers and video game consoles ran on a chip that cost less than a restaurant dinner. And remember Fagin, the engineer who had designed the 4004. True to the pattern we talked about, he left Intel and founded Zilog, where he designed the Z80, a processor that would power the Sinclair Spectrum, the Radio Shack TRS-80, and countless arcade games, from Pac-Man to Donkey Kong. The 1970s and early 80s became a golden age of microprocessors. Multiple companies competing fiercely, driving down costs and driving up capabilities. Home computers went from exotic toys for hobbyists to mass-market products. Software ecosystems emerged. Word processors, spreadsheet programs, and games created demand that pushed the hardware forward. And then, IBM entered the picture. In 1981, IBM released the IBM PC, powered by an Intel 8088 processor and running an operating system called MS-DOS that IBM had licensed from a small company in Seattle called Microsoft. The IBM PC was an instant success, and because IBM had used off-the-shelf components and published the technical specifications, other companies could build compatible machines. Within a few years, the market was dominated by IBM-compatible PCs, all running Intel processors, all running Microsoft software. This created the dynamic that would dominate personal computing for decades.
Each new Intel chip was faster than the last, consumed more transistors, required more advanced manufacturing, and reinforced the cycle described by Moore's law. The Intel 8286 gave way to the 8386, which gave way to the 8486. Each one faster, more complex, more capable. The naming convention eventually ran into a problem. Intel could not trademark a number, and competitors like AMD and Cyrix were releasing their own chips with the same numerical names. So when the time came for the next generation, Intel chose a word instead of a number: the Pentium. The Pentium, released in 1993, was a sensation. It used over 3 million transistors, roughly 1,000 times more than the original 4004 from just 2 decades earlier.
It was so fast that the rest of the computer struggled to keep up with it. A problem that drove innovation in memory, storage, and graphics hardware, as manufacturers raced to feed the processor's appetite. By the early 90s, Intel was the center of the computing universe, and the race to pack more transistors onto chips was accelerating. Competitors rose and fell. AMD became Intel's most persistent rival, offering comparable performance at lower prices. Companies like Cyrix found niches and then disappeared. The processor market became an arms race driven by Moore's law, with each new generation expected to deliver roughly double the transistors and correspondingly higher performance. The walls, as always, kept coming, and the next wall was about the most fundamental tool in the chipmaker's arsenal: the light they used to draw the circuits. Remember what Robert Noyce figured out? You could build a circuit layer by layer on a piece of silicon using photographic techniques. Light passes through a stencil. The pattern is projected onto the silicon surface, and you use that pattern to modify the material, etching away some parts, adding material to others, building up the circuit one layer at a time. That process has a name. It is called photolithography, and understanding how it works is absolutely essential to understanding how every computer chip gets made. So let us walk through it carefully. You start with a wafer of silicon, and this is where the story of sand really becomes remarkable. So let me slow down and walk through it, because the transformation from dirt to chip starts right here. The silicon in a computer chip cannot just be any silicon. Beach sand is mostly silicon dioxide, silicon atoms bonded to oxygen atoms, and it is full of impurities. Traces of iron, aluminum, calcium, dozens of other elements mixed in. To make a chip,
you need silicon that is almost unimaginably pure.
We are talking about purity levels of 99.9999999%. 9 nines. That means for every billion silicon atoms, you can tolerate at most one atom that is not silicon. 1 in a billion. If you had a pile of 1 billion grains of sand and one of them was a different color, that would be too many. To get silicon that pure, you start by converting the raw silica into a form called metallurgical grade silicon, which is about 98% pure. Then you put it through a chemical process involving hydrogen and chlorine to create a volatile compound called trichlorosilane. This compound is distilled repeatedly, each pass stripping away more impurities until the trichlorosilane is extraordinarily pure. Then you convert it back into solid silicon through a process called the Siemens process, where the gas is deposited onto heated rods in a sealed reactor. But even that is not enough.
To make chips, you need the silicon atoms arranged in a perfect crystal lattice. A single, unbroken grid of atoms extending through the entire piece, with no grain boundaries, no dislocations, no irregularities. You need a single crystal. And to grow one, the industry uses a process called the Czochralski method, named after the Polish scientist who developed it in 1916. Here is how it works. You melt the purified silicon in a crucible at about 2500 degrees Fahrenheit. Then, you dip a small seed crystal, a tiny piece of silicon that is already in the correct crystal structure, into the surface of the melt. And you slowly, very slowly, pull it upward while rotating it. As the seed rises, molten silicon crystallizes onto its bottom surface, extending the crystal structure of the seed into the new material. Over the course of many hours, you pull a large, cylindrical ingot of single crystal silicon out of the melt, sometimes 5 or 6 feet long and 12 inches in diameter. That ingot is then sliced into thin wafers using a diamond-tipped wire saw, and each wafer is polished to an almost unimaginable smoothness. If you scaled one of these wafers up to the size of a football field, the biggest bump on its surface would be a fraction of an inch tall. The surface is so flat and so clean that individual dust particles become a serious concern, which is why chip fabrication takes place in clean rooms, where the air is filtered to remove virtually all particles, and workers wear full-body suits that look like something from a science fiction movie. That level of flatness and purity matters because the features you are going to print on this surface are unbelievably tiny, and any imperfection in the substrate would ruin everything. A single stray atom in the wrong place can disrupt the behavior of a transistor. A single dust particle can block a feature and create a defect. The margin for error is essentially zero. Now you coat this wafer with a thin layer of a special material called photoresist. Think of it like the coating on photographic film. It is a chemical that changes its properties when light hits it. In one common type, called positive resist, the areas exposed to light become soluble and can be washed away with a chemical developer. The unexposed areas remain behind, so you are using light to create a pattern. Exposed areas dissolve, unexposed areas stay. The pattern comes from a photomask, sometimes called a reticle. This is essentially a stencil, a plate of glass with an incredibly precise pattern of chrome deposited on it. The chrome blocks light. The clear areas let light through. The pattern on this mask is a magnified version of the circuit layout you want to create. typically 4 or 5 times larger than the final pattern, because the optical system in the lithography machine will shrink it down when projecting it onto the wafer. And that optical system, the lithography machine itself, is essentially the most precise projector ever built. Light passes through the mask, enters a lens system of extraordinary sophistication, gets reduced in size, and projects a sharp image of the circuit pattern onto the photoresist-coated wafer below. Then you develop the wafer. You wash it with a chemical solution. The exposed photoresist dissolves away, leaving a pattern of bare silicon and remaining resist that exactly matches the design on your mask. And then you use that pattern to do something to the silicon underneath. Etch a trench, implant atoms, deposit a new material.
Each step modifies the wafer in a specific way, adding another piece to the three-dimensional puzzle. Then you strip off the remaining resist, coat the wafer with fresh resist, align a new mask with a different pattern, expose it, develop it, and do the next step. Layer after layer after layer. A modern chip might go through this cycle dozens of times, each layer adding another element of the structure. It is like building a city one floor at a time, using a different blueprint for each floor. Now, here is where the wall shows up. And it is a wall made of physics itself. The fundamental limit on how small you can print is determined by the wavelength of the light you are using. You cannot print features much smaller than the wavelength of your light source. For the same reason, you cannot write your name with a paintbrush wider than the letters.
The light has a resolution limit, and as you try to push features below that limit, the patterns blur and smear together, like trying to focus a flashlight beam to a pinpoint. There is a minimum spot size, and physics says you cannot go smaller. In the early days, this was not a problem. Chip makers used ordinary visible light, and the features they were printing were measured in micrometers, which is millionths of a meter, or roughly 1/25,000th of an inch. Visible light has a wavelength of roughly 400 to 700 nanometers, and features of a micrometer or more were well within reach. But as transistors shrank through the 1970s and 80s, the industry started bumping against the resolution limit. They needed finer detail, and that meant shorter wavelengths, because shorter wavelengths give you a sharper focus, just like a fine-tipped pen lets you write smaller letters than a thick marker.
So they moved from visible light to ultraviolet light. By the mid-80s, they were using what is called G-line light at 436 nanometers. Then they shifted to I-line at 365 nanometers. Then, in the 90s, they made the jump to deep ultraviolet, or DUV. First at 248 nanometers, using krypton fluoride lasers, and then at 193 nanometers, using argon fluoride lasers. Each of these transitions was a massive engineering effort, worth emphasizing just how massive. New light sources had to be developed. New lens materials were needed because ordinary glass absorbs deep ultraviolet light. So engineers had to turn to exotic materials like calcium fluoride and fused silica. New photoresist chemistries had to be invented. New mask-making techniques had to be perfected. Billions of dollars of research and development, entire careers dedicated to moving from one wavelength of light to a slightly shorter one. And at every step, people predicted the end was near. Serious, credentialed people argued that the limits of physics were approaching. In the 1980s, there were physicists who said that feature sizes below 1 micrometer were simply impractical. In the 90s, they said the same about a 1/4 micrometer. And every single time, engineers found a way. Sometimes the way around was brute force,
just switch to a shorter wavelength. But increasingly, the industry developed a bag of astonishingly clever optical tricks that let them print features far smaller than the wavelength of the light itself. One of the cleverest was called optical proximity correction. Here is the idea. When you try to print very small features, the light diffracts. It bends around edges and interferes with itself, and the pattern you get on the wafer does not look exactly like the pattern on your mask. Corners get rounded, lines get thicker or thinner than they should. Features that are close together interact with each other in unpredictable ways. So what engineers did was deliberately distort the pattern on the mask, adding little extra bumps and notches, features that did not correspond to anything in the real circuit design. So that after the light diffracted and interfered and did all its messy wave things, the final pattern on the wafer came out correct. They pre-compensated for the distortion. Think of a golfer aiming left because they know the wind is going to push the ball right. The mask is intentionally wrong so that the result is right. Then there was immersion lithography, which appeared around 2006 and was a genuine game changer. The idea is simple in concept, though hideously difficult in practice. Instead of having air between the lens and the wafer, you fill that gap with ultra-pure water.
Water has a higher refractive index than air, which effectively shortens the wavelength of light as it passes through, giving you finer resolution without changing the light source. You are still using the same 193 nanometer argon fluoride laser, but the water makes it behave as if it were closer to 134 nanometers. This one trick extended the useful life of 193 nanometer lithography by years, pushing it far beyond what anyone had thought possible. Combined with optical proximity correction, off-axis illumination, and phase shift masks, the industry squeezed an almost absurd amount of performance out of 193 nanometer light. But perhaps the most dramatic extension technique was multiple patterning. The idea behind multiple patterning is conceptually simple, but practically brutal.
If you cannot print a fine enough pattern in a single exposure, because the features are too close together for your light to resolve, you split the pattern into 2 or more separate exposures. In double patterning, you print every other line in the first exposure, shift the mask, and print the remaining lines in a second exposure. Each individual exposure has features that are comfortably within the resolution limit. But when you overlay the 2 exposures, the final pattern is twice as dense as either one alone. Triple patterning and quadruple patterning take the same logic further, splitting a single layer into 3 or 4 separate exposures. Each one requires its own mask, its own alignment, its own processing steps. The cost and complexity multiply dramatically. A single layer that used to require 1 mask and 1 exposure now needs 4 masks and 4 exposures, with extraordinarily tight alignment between them. A few nanometers of misalignment between exposures, and the pattern is ruined. Multiple patterning worked, and it carried the industry from the 32 nanometer node all the way down to around 7 nanometers before EUV finally took over for the most critical layers. But it was a brute force solution, expensive and time-consuming. A wafer that went through quadruple patterning for its most critical layers took significantly longer to process, used significantly more masks, and cost significantly more than one that used single exposure. The industry was essentially compensating for the limits of its light source by doing 4 times the work. It was clever, it was effective, and it was unsustainable. Everyone knew that multiple patterning was buying time, not solving the fundamental problem. But there is a point where no amount of cleverness can push 193 nanometer light any further. The tricks pile up. The process becomes more complex. The number of exposures per layer doubles and then doubles again. The cost spirals upward, and eventually you are spending more effort fighting the physics than actually making chips. The optical gymnastics that had carried the industry for 2 decades were running out of room. Everyone in the industry knew this wall was coming. They had known for a long time, decades actually, and they had been working on the next solution for just as long. But that next solution was so technically ambitious, so outrageously difficult, that many smart people genuinely believed it would never work. Because to go smaller, you needed a type of light that barely exists in nature. You needed mirrors polished to the smoothness of individual atoms. You needed to vaporize 50,000 droplets of molten tin per second with a high-powered laser, creating a miniature star inside a vacuum chamber, and harvest one very specific wavelength from the resulting plasma. And you needed to do all of this reliably, hour after hour, day after day, inside a machine that weighs about 400,000 pounds and costs more than a commercial airliner. That machine has a name, and the story of how it came to exist is one of the most extraordinary engineering achievements in human history. The letters EUV stand for extreme ultraviolet, and the extreme part is not marketing hype. The wavelength of EUV light is 13.5 nanometers. The previous generation of lithography worked at 193 nanometers, and even that required water immersion tricks to behave like 134. 13.5 is more than 14 times shorter.
And in lithography, shorter wavelength means finer features, which means more transistors, which means faster, more powerful, more efficient chips. The motivation was clear. The problem was everything else. Let us start with the light source, because it is genuinely astonishing. You cannot make a laser that directly outputs 13.5 nanometer light, at least not with enough power to be useful in a factory setting. The physics does not cooperate. So the engineers who designed EUV lithography had to find another way to generate photons at that specific wavelength. The method they came up with sounds like something from a science fiction novel. Inside the EUV machine, there is a chamber where tiny droplets of molten tin fall through a vacuum. We are talking about 50,000 droplets per second, each one roughly 25 micrometers across, about the diameter of a thin human hair. As each droplet falls, it gets hit by a pulse from a high-powered carbon dioxide laser. And hit is an understatement. The laser strikes each droplet twice. The first pulse flattens the droplet into a pancake shape, optimizing its geometry. The second pulse, much more powerful, vaporizes it completely, heating the tin to roughly 900,000 degrees Fahrenheit. At that temperature, the tin atoms lose many of their electrons and become a plasma, a super-hot cloud of ions. And that plasma radiates light across a range of wavelengths, including the precious 13.5 nanometers. So you are creating a tiny star, 50,000 times per second inside a vacuum chamber and collecting one specific color of light from the glow. The precision required is beyond description. Each droplet has to be in exactly the right place when the laser hits it. The laser has to fire at exactly the right moment. The energy delivery has to be precisely calibrated.
If anything is off by even a tiny fraction, the droplet does not produce usable light, and you have wasted 1/50,000th of a second. Which does not sound like much, but when you are trying to expose 125 wafers per hour, every wasted pulse adds up. But generating the light is only the beginning. Here is a deeply inconvenient fact about 13.5 nanometer light. It gets absorbed by almost everything. Air absorbs it, Glass absorbs it. Any conventional lens material absorbs it. This means you cannot use lenses at all. Every previous generation of lithography was built around lenses, refractive optics, light passing through transparent materials. EUV threw all of that away. The entire optical path uses mirrors instead. And these mirrors are not ordinary mirrors. They are made from alternating layers of molybdenum and silicon, each layer just a few nanometers thick, stacked up in about 40 pairs.
This structure creates what physicists call a Bragg reflector, a multi-layer coating that can bounce EUV light instead of absorbing it. But even with this clever design, each mirror only reflects about 70% of the light that hits it. The other 30% is absorbed and lost. There are about 11 mirrors in the optical path between the light source and the wafer. If each one reflects 70%, and you multiply that out over 11 reflections, only about 2% of the original light actually reaches the wafer. 2%. Which is why you need such an incredibly powerful light source to begin with. You are generating an enormous amount of light and accepting that 98% of it will be absorbed along the way, just to get enough photons to the surface of the silicon. And the surface quality of these mirrors is where the story moves from impressive into genuinely mind-bending.
The mirrors must be polished to a smoothness measured in fractions of a nanometer. The specification is typically less than 50 picometers of roughness. A picometer is a trillionth of a meter. To put that in perspective, if you scaled one of these mirrors up to the size of Germany, a country roughly 560 miles across, the tallest bump on its surface would be shorter than the thickness of a credit card. A company called Zeiss, the famous German optics manufacturer, makes these mirrors, and they are among the most precisely shaped objects in human existence. Because EUV light is absorbed by air, the entire beam path inside the machine operates in a near-perfect vacuum. And the mask, the stencil that carries the chip pattern, also has to be reflective rather than transmissive, because you cannot shine EUV light through glass. The mask is itself a multi-layer mirror with the circuit pattern defined on its reflective surface, and it must be kept absolutely free of contamination, because even a single particle a few nanometers across can create a defect in the final pattern. Protecting EUV masks from contamination was one of the hardest sub-problems in the entire development effort. When you add all of this up, the plasma light source, the multi-layer mirrors, the vacuum environment, the reflective masks, the contamination control, you begin to understand why EUV lithography took so long. The concept was first seriously proposed in the late 1980s. Research programs began at national laboratories in the United States, at Lawrence Livermore and Sandia, with significant government funding. A consortium called EUV LLC was formed in 1997, bringing together Intel, AMD, Motorola, and others. And through the late 90s and the 2000s, progress was agonizingly slow. The early experimental setups could barely produce a visible spot of EUV light, let alone enough to expose a wafer. The tin plasma sources sputtered and failed. The mirrors degraded under the intense radiation. The masks accumulated defects that no amount of cleaning could remove. Each problem, when solved, revealed 3 more waiting behind it. There were entire conferences dedicated to EUV, where the dominant mood was something between cautious hope and quiet despair. The semiconductor industry had a backup plan, or rather, several backup plans. Some people pushed for electron beam lithography, which did not have a wavelength limit in the same way, but was far too slow for high-volume manufacturing. Others explored nano-imprint lithography, physically stamping patterns onto the wafer, like a microscopic printing press. Still others argued for extending 193 nanometer light even further, using ever more elaborate multiple patterning schemes.
None of these alternatives was ideal, and the industry kept betting on EUV, even as the years dragged on and the skeptics grew louder. What kept the program alive was a shared understanding that there was no better option. If EUV failed, Moore's law would stall, and the economic engine that had driven the technology industry for decades would seize up. The chip companies could not afford for EUV to fail. So they kept funding it, even when progress was measured in increments so small they were hard to celebrate. The company that finally pulled it all together was ASML, a Dutch firm headquartered in Veldhoven, a quiet town in the south of the Netherlands that most people have never heard of. And ASML did not do it alone. Zeiss built the mirrors. Kymer, a San Diego company that ASML eventually acquired, dramatically improved the tin droplet laser source, pushing its power from around 10 watts in the early prototypes up past 250 watts. Resist. Chemists developed new photosensitive materials optimized for EUV wavelengths. Mask makers developed better defect inspection tools. Dozens of companies and labs across multiple countries each solved their piece of the puzzle. ASML shipped its first prototype EUV systems around 2006 and 2010. But these were research tools, useful for experiments, but far too slow for manufacturing. The critical metric, the one that determined whether EUV would be economically viable, was throughput, how many wafers per hour the machine could process. For factories to justify the cost, the machine needed to hit around 125 wafers per hour. The early prototypes were stuck at a fraction of that, but the engineers kept pushing, and slowly, painfully, the numbers climbed. The light source got brighter, the mirrors got better, the contamination controls improved.
And around 2018, EUV finally entered high-volume manufacturing, first at Samsung and then at TSMC, for the most critical layers of chips at the 7nm and 5nm technology nodes. After roughly 30 years of development, 3 decades from concept to factory floor, a single EUV machine weighs about 400,000 pounds, contains more than 100,000 parts, and costs somewhere in the neighbourhood of $350 million. Some of the latest versions, called high-N AEUV, cost even more. There is exactly one company on the entire planet that makes them. ASML, in a small Dutch town you have probably never heard of, builds the machine without which no advanced chip can exist. If ASML stopped building these machines tomorrow, the world's most advanced semiconductor manufacturers would eventually grind to a halt.
Your phone, your laptop, the servers running the internet, the chips in cars and hospitals and power grids. All of it depends, ultimately, on this one company and this one machine. Think about that for a moment. The most complex and expensive factories ever constructed by human beings, the fabrication plants where the world's most advanced chips are made, are organized around this single tool. And the tool itself is a cathedral of engineering, a machine that creates miniature stars to generate a type of light that barely exists in nature, bounces it off mirrors polished to the smoothness of individual atoms, and uses it to print patterns on silicon in a vacuum. Patterns so small that a virus would look enormous next to them. And it all started with sand. But the lithography, as central as it is only one dimension of the challenge.
Because after you have used that impossibly precise light to print a pattern on the wafer, you still have to actually transfer that pattern into the silicon. You have to etch, deposit, implant, polish, and repeat dozens of times. with a precision that would have been considered sorcery a generation ago. And as features shrank below 50 nanometers, then below 20, then below 10, the transistor itself started to break down. The fundamental architecture of the switch, the way it had been designed since the very beginning, stopped working at these tiny scales. Physics was hitting back. And this time, the wall was not about light or manufacturing. It was about the transistor itself. For decades, the basic transistor design used in chips was remarkably simple. A flat slab of silicon, a thin insulating layer on top, and a metal gate electrode above the insulator. When you apply a voltage to the gate, the electric field passes through the insulator and into the silicon, pulling electrons toward the surface and creating a conductive channel. Current flows from one side to the other. Remove the voltage, the channel collapses and current stops. On and off. 1 and 0. This is called a planar transistor because everything happens on a flat plane. The channel where the current flows runs horizontally along the surface, and the gate sits on top like a lid, controlling what happens beneath it. This basic design, with countless refinements and optimizations, carried the semiconductor industry from the 1960s all the way to the early 2000s. 40 years of progress built on the same fundamental architecture. But there was a hidden problem, and it got worse as transistors got smaller. The insulating layer between the gate and the silicon channel is critical. It has to be thin enough for the electric field from the gate to reach through and control the channel, but it also has to be a good enough insulator to prevent current from leaking through it. For decades, that insulating layer was made of silicon dioxide, essentially glass. Silicon dioxide is easy to grow on silicon. It forms a nearly perfect interface, and it is an excellent insulator. It worked beautifully. But as transistors shrank, that silicon dioxide layer had to get thinner and thinner to maintain the gate's control over the channel. By the early 2000s, at the 90 nanometer and 65 nanometer technology nodes, the gate insulator had been whittled down to roughly 1 to 1.5 nanometers. That is about 5 atoms thick. 5 atoms standing between the gate and the channel. And at that thickness, something deeply strange starts to happen. Quantum mechanics kicks in.
Electrons, which are supposed to stay on their side of the insulating barrier, start tunneling through it. They do not have enough energy to climb over the barrier in the classical sense. They simply appear on the other side, as if they had passed through a wall. Because at quantum scales, particles have a probability of being found anywhere, and a 5-atom thick wall gives them a meaningful chance of getting through. This tunneling current is a leakage current. It means the transistor is wasting power even when it is supposed to be off, like a faucet that drips no matter how hard you turn the handle. And when you have 1 billion transistors on a chip, each one leaking a tiny bit, the total leakage power adds up to a real problem. The chip gets hot. It wastes battery. It becomes hard to manage. This was the wall. You could not make the insulator any thinner without electrons ghosting through it, and you could not keep it thick without losing the gate's ability to control the channel. The solution came in 2 parts, and both were major engineering milestones. First, the material. If silicon dioxide was too leaky at the thickness you needed, what about a different insulating material? One with a higher dielectric constant, meaning it could sustain a stronger electric field for a given thickness. A higher dielectric constant lets you use a physically thicker layer, which blocks tunneling, while getting the same electrical behavior as a thinner layer of silicon dioxide. You get the insulation you need without the quantum mechanical leakage. The material the industry settled on was hafnium dioxide, a compound of the metal hafnium, element 72 on the periodic table. Hafnium dioxide has a dielectric constant roughly 5 to 6 times higher than silicon dioxide. That means you can use a layer 5 or 6 times thicker and get the same electrical performance.
The thicker layer slams the door on tunneling. But depositing that hafnium dioxide layer required a technique called atomic layer deposition, or ALD, which is one of those processes that is so elegant it makes you pause when you understand it. Instead of spraying material onto the wafer all at once and hoping it goes everywhere evenly, ALD deposits material one atomic layer at a time. You pulse in a gas that bonds to the surface and then stops because all the bonding sites are filled. You flush that gas away. Then you pulse in a second gas that reacts with the first, completing one atomic layer. Flush, repeat. Each cycle deposits exactly one layer of atoms. You can control the thickness to the precision of a single atom, and the coating covers every surface uniformly, even the bottoms of deep, narrow trenches. Intel was the first to introduce high-K metal gate transistors, using hafnium dioxide deposited by ALD in volume production in 2007 at the 45 nanometer node. It was the biggest change in transistor materials in decades. But the material fix was only half the solution. The other half required rethinking the shape of the transistor itself. Remember, a planar transistor has the gate sitting on top of a flat channel, like a lid on a pot. The gate only controls the channel from one side, the top. As the channel gets shorter and narrower, the gate's control weakens. It is like trying to hold a hose with one hand. The shorter the hose, the more likely the water will spray out the sides, no matter how hard you squeeze. The answer was to wrap the gate around the channel from more than one side. And to understand why that helps, think about it this way. Imagine you are trying to squeeze a garden hose shut with your fingers.
If you pinch it from only one side, the top, the water can still sneak through the bottom and the edges. But if you can wrap your hand around the hose, squeezing from 3 sides, you have much better control. You can stop the flow completely when you want to, and let it through precisely when you choose. That is essentially what the industry did, starting around 2011. They stood the channel up on its edge. Instead of a flat ribbon of silicon running horizontally along the surface, the channel became a thin, vertical fin of silicon sticking up from the chip, like a shark's fin rising from the water. The gate material wrapped around 3 sides of this fin, top and both sides, giving the gate much better electrostatic control over the current flowing through the channel. This design was called FinFET because the channel was shaped like a fin. Intel introduced it at the 22 nanometer node, and TSMC and Samsung followed with their own versions.
FinFETs gave the industry another decade of scaling, carrying chip technology from 22 nanometers down to around 5 nanometers. But even FinFETs have limits. As the fin gets narrower and the dimensions shrink further, the gate still cannot control the channel from all directions. 3 sides are better than 1, but 4 would be better than 3. And that is where the industry is heading now. The next transistor architecture, already in production at some companies, is called gate-all-around. Instead of a fin, the channel becomes a series of thin, horizontal ribbons or sheets of silicon, stacked on top of each other, with the gate material wrapping completely around each one. The gate touches the channel on all 4 sides, giving the best possible electrostatic control. Manufacturing gate-all-around transistors is, as you might expect, extraordinarily complex.
You grow alternating layers of silicon and silicon germanium. Then selectively etch away the silicon germanium to release the silicon sheets. Then deposit gate material all the way around them with atomic-level precision. 20 years ago, this would have seemed impossible. And honestly, it still feels that way, even now that people are doing it in factories. But here is the part I want to linger on, because it connects to something deeper. With each of these transitions, from planar to FinFET to gate-all-around, the number of people who could look at a chip design and fully understand every transistor on it dropped. It was not that people got less smart. The designs got more complicated faster than any individual mind could follow. In the early 1960s, when integrated circuits had a few dozen transistors, engineers drew the designs by hand.
They sat at drafting tables with colored pencils and rulers, literally sketching each transistor and each wire on large sheets of paper. They knew every component. They could explain what each one did and why it was there. By the late 1970s, chips had tens of thousands of transistors, and hand drawing was no longer possible. Software tools emerged to help, programs that could translate high-level descriptions of what a circuit should do into detailed layouts of how to build it. Engineers started describing circuits in terms of their function, and computers translated those descriptions into geometry. By the 2000s, chips had hundreds of millions of transistors. No human could hold the design in their head. The design was done by teams of hundreds of engineers, using software tools that were themselves enormously complex. Tools built by other teams of hundreds of engineers. The tools translated descriptions written in hardware description languages into networks of logic gates, optimized the placement and wiring, checked timing, verified functionality, and generated the mask data for the lithography machines. Today, a cutting-edge chip might contain over 100 billion transistors. The design team is 1,000 people working for 3 to 5 years. The cost of designing a single chip at the most advanced nodes, when you add up engineering salaries, software licenses, mask costs, and test silicon, can exceed $1 billion. The software tools that turn the design into a physical chip are among the most computationally demanding programs in existence, requiring weeks of compute time on clusters of powerful servers. Two companies, Synopsys and Cadence, dominate the market for these tools, and their software is so essential that the entire semiconductor industry depends on them. The process works in layers of abstraction. An engineer writes a description of what the chip should do in a hardware description language, something like Verilog or VHDL. A synthesis tool translates that description into a network of logic gates. A place and route tool figures out where to put each gate on the chip and how to wire them together through those dozen-plus layers of metal interconnect, without any wires crossing where they should not, without any signal arriving too late, without any area getting so congested that the physical routing becomes impossible. The place and route problem is, mathematically speaking, NP-hard, meaning there is no known algorithm that can find the perfect solution in reasonable time. The tools use sophisticated heuristics, clever approximations, to find solutions that are very good, even if not perfect. And then there is verification, which consumes 60 to 70% of the total engineering effort. A bug in a chip with 100 billion transistors cannot be fixed with a software update, the way you would patch a program. A flawed chip means a flawed mask set, and a mask set at the most advanced nodes costs $15 to $20 million. One mistake that slips through verification, and you have burned tens of millions of dollars and months of time. So engineers write millions of lines of test code, run billions of simulation cycles, and use formal mathematical methods to prove that certain classes of bugs cannot exist. And still, first silicon almost always has some bugs, which is why modern chips are designed with built-in workarounds, spare circuits, programmable fuses, and updatable microcode that can compensate for problems discovered after manufacturing. We build these things with computers designing computers, a recursive loop that would have been unimaginable to Kilby or Noyce or Bardeen or anyone who worked with those early circuits in the 1960s.
The complexity has outrun any single human mind. And yet the chips work. They work with extraordinary reliability. Billions of transistors switching billions of times per second, hour after hour, year after year. That gap between what any one person can understand and what the collective enterprise can produce, that is worth sitting with. Because it says something important about how human civilization works at its most impressive. We did not get here because any one person was smart enough to design a modern chip. We got here because thousands of people, each mastering one tiny piece of the puzzle, figured out how to connect their pieces together, generation after generation, decade after decade, each group standing on the shoulders of the one before. But there is another dimension to chip making that we have not talked about yet, and it is just as important as the transistors and the lithography. Because once you have built your billions of tiny switches, you need to connect them to each other. And the wiring, it turns out, is its own world of challenges. If you could slice a modern chip in half and look at it from the side, what you would see might surprise you. The transistors are at the very bottom, a thin layer sitting right on the silicon surface, and above them, towering over them, is a skyscraper of metal wiring, layer after layer of copper traces embedded in insulating material, connected by tiny vertical pillars called vias. A modern high-performance processor might have 12, 14, 16 or more layers of metal wiring stacked on top of each other. The bottom layers, closest to the transistors, have the finest, most tightly packed wires, because those are making short, local connections between nearby transistors. As you go up, the wires get wider and the spacing gets more generous, because those upper layers carry signals over longer distances or distribute power across the whole chip. The very top layers might have wires a few micrometers wide, while the traces at the bottom might be only 20 or 30 nanometers across. The total length of wiring on a modern chip, if you could unravel it and lay it out in a straight line, would stretch for miles. Miles of copper, inside a chip the size of your thumbnail, connecting billions of transistors in precisely the right pattern. For decades, that wiring was made of aluminum. Aluminum is a decent conductor, easy to work with, and the industry had deep experience using it. But as chips got faster and wires got thinner, aluminum started hitting a limit. Its electrical resistance is about 40% higher than copper's, and at nanometer scales, that extra resistance means signals take longer to travel through the wires, and more energy is wasted as heat. The wiring delay was actually becoming a bigger bottleneck than the transistor switching speed itself. The obvious answer was to switch to copper. Copper is a better conductor, period. But copper presented a genuinely terrifying problem. Copper atoms are fast diffusers in silicon. If copper gets into the active transistor regions, it creates traps that destroy the transistor's electrical behavior. Copper is essentially poison to silicon devices. And copper is much harder to etch with plasma processors than aluminium, which means you cannot just deposit a layer of copper and cut it into wires the way you could with aluminum. The solution came from IBM in 1997, and it had a wonderfully poetic name, the Damascene process. Damascus, the ancient Syrian capital, was famous for a metalworking technique in which craftsmen would carve grooves into steel and then inlay gold or silver wire into those grooves, creating intricate decorative patterns on sword blades. The semiconductor Damascene process works on exactly the same principle, adapted to the nanometer scale.
Instead of depositing copper and then etching it into wires, you first etch trenches into the insulating layer. You carve the pattern of the wires into the insulation. Then you deposit a thin barrier layer, typically tantalum and tantalum nitride, to line those trenches and prevent copper from escaping into the surrounding material. Then you deposit a thin copper seed layer, and then, remarkably, you fill the rest of the trench using electroplating, the same basic electrochemistry that has been used to plate jewelry and car bumpers for over a century. You dip the wafer into a copper sulfate solution, run a current, and copper ions deposit onto the seed layer, filling the trenches from the bottom up. Once the trenches are overfilled, you polish off the excess with chemical-mechanical planarization, a process that is exactly what it sounds like, a very precise, very controlled polishing operation that grinds the surface perfectly flat, leaving copper wires inlaid in an insulating matrix contained by barrier layers, with a perfectly smooth surface ready for the next layer. Let me dwell on the etching for a moment, because it is a good window into the kind of precision we are talking about. In the early days of chip making, etching meant dipping the wafer into a chemical bath. An acid would dissolve the exposed material, and the photoresist would protect the parts you wanted to keep. Simple. But liquid chemicals do not care about direction.
They eat sideways, just as happily as they eat downward, which means your features get undercut. The acid crawls under the edges of the resist, rounding corners, widening trenches, making everything a little bit sloppier than the pattern you drew. When features are measured in micrometers, that sloppiness is tolerable. When they are measured in nanometers, it ruins everything. So the industry moved to dry etching, specifically plasma etching. Instead of a liquid, you use an ionized gas, a plasma, inside a vacuum chamber. The wafer sits on an electrode, and reactive ions from the plasma are accelerated downward by an electric field. Because they are traveling in a predominantly vertical direction, they etch downward much faster than sideways. You get clean, vertical walls, the kind of sheer cuts that nanometer scale features demand. But controlling a plasma etch at this scale is extraordinarily delicate. You have to manage the gas chemistry, the pressure, the power levels, the temperature, and the timing, and you have to do it uniformly across an entire 12-inch wafer. Any variation in etch rate from the center of the wafer to the edge means some transistors come out slightly different from others, and at these scales, slightly different can mean the difference between a working chip and scrap. The engineers who develop etch processes call their specifications recipes, like cooking, and tuning a recipe to get the uniformity and precision needed for modern chips is painstaking work that can take months. And etching is just one step. After you carve a trench, you often need to fill it with something. A metal conductor, an insulating layer, a thin barrier to prevent atoms from migrating where they should not. Depositing materials into tiny features requires its own set of techniques. Chemical vapor deposition flows reactive gases into a chamber where they break apart and form a thin, solid film on the wafer surface, atom by atom, like condensation on a cold window. Physical vapor deposition bombards a target material with energetic ions, knocking atoms loose and letting them fly across a vacuum to coat the wafer, like splattering paint off a wall. And for the thinnest, most critical layers, there is atomic layer deposition, which we talked about earlier, depositing material one atomic layer at a time with angstrom-level control. Each of these techniques has its own strengths and limitations, and modern chip manufacturing uses all of them, chosen step by step based on what each specific layer requires. The combination of techniques involved in this single process, lithography, plasma etching,
physical vapor deposition, electroplating, chemical, mechanical polishing. Each one a deep discipline in its own right, and all of them working together at nanometer precision, is a good illustration of why chip manufacturing is so hard. It is not that any single step is impossibly difficult in isolation. It is the cumulative orchestration of hundreds of steps, each demanding its own kind of perfection, stacked on top of each other in a sequence where a mistake at step 200 can ruin everything that came after. And with every generation of chips, the wires got thinner, the layers got more numerous, and the challenges compounded. The resistance of copper wires increases as they get thinner, because the electrons start scattering off the surfaces and grain boundaries of the metal, losing energy. The capacitance between wires increases as they get closer together.
Resistance times capacitance gives you what engineers call RC delay, the time it takes a signal to propagate down a wire, and as wires shrank, RC delay became the dominant performance limiter. Your transistors could switch in picoseconds, but the signals spent most of their time crawling through skinny wires. The highway became the bottleneck, not the cars. To fight this, engineers also changed the insulating material between the wires. Traditional silicon dioxide has a dielectric constant of about 3.9, and that contributes to the capacitance. So the industry developed low-K dielectrics, materials with lower dielectric constants. Carbon-doped silicon oxide, porous materials that incorporated tiny air pockets to bring the dielectric constant down toward 2. Air itself has a dielectric constant of 1, so the more porosity you can introduce, the better. But porous materials are mechanically fragile, like a sponge at the molecular level. And they still have to survive the harsh polishing and chemical treatments of the manufacturing process. Making an insulator that was electrically excellent, but also mechanically tough enough to survive manufacturing, was one of the quieter but deeply consequential engineering challenges of the 2000s and 2010s. All of this, the transistors at the bottom, the towering stack of metal wiring above, the carefully chosen materials at every layer, sits on a silicon wafer that has been processed for 2 to 3 months by the time it is done. Hundreds of machines, thousands of individual process steps, and a single wafer full of cutting-edge processors can be worth tens of thousands of dollars. But even after all those weeks of painstaking fabrication, you are not finished. Because right now, all you have is a wafer full of chips that you hope work. And hope is doing a lot of work in that sentence. Here is the reality of semiconductor manufacturing, and it is a reality that never goes away no matter how good the process gets. Not every chip on the wafer works. Some have defects. A particle of dust that landed on the wafer during one of those hundreds of processing steps. A slight variation in etching that caused a wire to be too thin in one spot. A void in a copper fill. A gate insulator that is a fraction of a nanometer too thick. Any one of 1,000 things can go wrong. And when you are dealing with features measured in nanometers and billions of components on each chip, the statistical certainty is that some fraction of your chips will have fatal defects. The percentage of chips that actually work is called yield, and yield determines everything about the economics of chip manufacturing. A new process might start with yields of 30 or 40%, meaning more than half the chips are scrap. As engineers find and fix problems, yields climb. A mature process might reach 85 or 90%. Getting from that early low yield to a high, stable yield is called yield ramp, and it is one of the most intense, high-pressure phases in the entire industry. The people who do this work are essentially detectives. They spend their days staring at defect maps, which are plots showing where on the wafer the bad chips are located. And the patterns on those maps tell stories. If the defects cluster around the edges of the wafer, that might indicate a problem with how a chemical is flowing in a deposition chamber. If they form a streak, Maybe a particle got caught on a transport mechanism. If they are scattered randomly, you might be dealing with airborne contamination in the clean room. Every defect is a clue, and tracing it back to its root cause through hundreds of process steps is genuinely one of the hardest diagnostic challenges in all of engineering.
The tools they use for this investigation are remarkable. Optical inspection machines scan the wafer surface with laser light, looking for scattered photons that indicate particles or pattern irregularities. Electron beam inspection systems, essentially scanning electron microscopes adapted for high-speed wafer scanning, can spot defects too small for optical detection, features just a few nanometers across. There are tools that measure film thickness to sub-angstrom precision, tools that measure the width of wires using a technique called scatterometry, where you bounce light off a repeating pattern and analyze the way it diffracts to infer the dimensions. All of this data feeds into massive databases, and the analysis increasingly uses machine learning to find correlations that human analysts might miss. A yield engineer might discover that wafers processed in a particular etching chamber on Tuesday afternoons have a slightly higher defect rate, and trace it back to a maintenance procedure that was done slightly differently that day, or a gas flow controller that was drifting out of its calibration range. The detective work is meticulous, statistical, and never-ending, because a process that has been running perfectly for months can suddenly develop a new defect mode when a batch of chemicals from a new supplier arrives, or when a seal in a vacuum chamber degrades by a fraction of a millimeter. The pursuit of yield is relentless because the economics demand it. At a leading-edge fab that cost $20 billion to build, every percentage point of yield improvement translates directly to the bottom line. A fab running at 85% yield produces significantly more revenue from the same wafers than one running at 80%. The difference between a profitable product and a money-losing one can literally come down to a few percentage points of yield. Once the good chips have been identified, the wafer is cut apart, either with a diamond-tipped saw or a laser, and each working chip, called a die, is packaged. And packaging, which for decades was treated as an afterthought, the boring last step before shipping, has become its own frontier of innovation. Because the chip, by itself, is incredibly fragile. It is a thin sliver of silicon, maybe 3/4 of a millimeter thick, with billions of transistors and a dozen layers of copper wiring built into its top surface. It cannot communicate with the outside world except through tiny metal pads on its surface, and those pads need to be connected reliably to something larger and more robust, something you can solder onto a circuit board and plug into a computer.
The classic approach was wire bonding. Glue the chip face up onto a metal frame and use impossibly thin gold or copper wires, thinner than a human hair, to connect each pad on the chip to a lead on the frame. A machine called a wire bonder does this, forming tiny ball bonds with a combination of heat, pressure, and ultrasonic vibration, about 15 to 20 connections per second. Then, the whole assembly gets sealed in epoxy resin. That is your standard black plastic chip package. But for high-performance chips, wire bonding has limitations. Each wire is a tiny antenna, a tiny source of resistance and inductance. When signals run at gigahertz frequencies and you need thousands of connections, those wire loops matter. So the industry moved to flip chip bonding, where the chip is flipped upside down and connected directly to the substrate through an array of tiny solder bumps across its entire bottom surface, not just around the edges.
More connections, shorter paths, better electrical performance. The substrate that the die gets flip-chipped onto is itself a miniature circuit board with multiple layers of its own wiring that route signals from the dense bump pattern underneath the chip out to the larger solder balls on the bottom of the package, which are what actually connect to the main circuit board in your computer or phone. This substrate might have 8 or 10 or 12 layers. It redistributes connections, manages power delivery, and sometimes includes embedded capacitors, little energy reservoirs built right into the package to smooth out the rapid current fluctuations that happen when billions of transistors switch simultaneously. And the thermal challenge is enormous. A modern high-performance chip might generate 200 or 300 watts of heat, all concentrated in an area the size of your thumbnail.
That heat has to go somewhere, or the chip will throttle itself and slow down, or worse, sustain damage. The package includes a heat spreader, usually a copper lid, attached to the top of the die with a thermal interface material, designed to conduct heat away from the concentrated hotspot and spread it over a larger area where a fan or heat sink can carry it off. Some high-end packages use indium solder as the thermal interface instead of paste because it conforms perfectly and conducts heat much better. It sounds like a small detail, but engineers have spent entire careers optimizing thermal interfaces because if you cannot get the heat out, nothing else matters. And then, in one of the most consequential shifts in recent chip history, the industry began breaking chips into pieces.
Instead of making one enormous chip, which gets more expensive and harder to manufacture as it gets bigger, you could make several smaller chips, called chiplets, each optimized for its function, and connect them together inside an advanced package. The processor cores might be on one chiplet made with the most advanced, most expensive manufacturing process, while the input-output controllers sit on a separate chiplet made with an older, cheaper process, because they do not need tiny transistors. AMD proved this approach could work at scale with their Zen 2 architecture in 2019. They put multiple small CPU chiplets alongside a larger input-output die in a single package. The CPU chiplets were made on TSMC's cutting-edge 7nm process. The I/O die was made on a more mature 12nm process. The small chiplets had high yields because smaller chips are less likely to have a random defect land on them. The I/O die could be big and cheap because it used an older, less expensive process. AMD got leading-edge performance where it mattered most without paying the cost penalty of putting everything on the most expensive node. But connecting chiplets introduces its own challenges. The connections between them need to be fast, numerous, and energy efficient. If you connect chiplets through the package substrate alone, you are limited by the wiring density of that substrate, which is much coarser than the wiring inside a chip. So the industry developed silicon interposers, thin pieces of silicon with very fine wiring etched into them that sit between the chiplets and the package substrate. Because the interposer is made using semiconductor lithography, its wiring can be far denser than anything achievable in an organic substrate. TSMC's CoWoS technology, which stands for chip on wafer on substrate, uses exactly this approach and has become essential for high-performance applications. When you hear about the latest AI accelerators from NVIDIA, chips that cost tens of thousands of dollars apiece, many of them use CoWoS or something similar to connect the processor die to stacks of high-bandwidth memory. The packaging technology is as much a competitive advantage as the transistor technology itself. And then there is three-dimensional stacking, where instead of placing chips side by side, you stack them vertically. High-bandwidth memory, which is used in the AI accelerators and graphics processors that are currently reshaping the technology landscape, is built this way. Multiple layers of memory chips, 4, 8, even 12 layers, stacked on top of each other,
connected by thousands of tiny copper pillars punched straight through the silicon, called through-silicon vias. A through-silicon via is exactly what it sounds like, a hole drilled straight through the silicon die, filled with copper, creating a direct electrical path from one layer to the next. The result is enormous memory bandwidth in a tiny footprint, because instead of spreading memory across a wide area of a circuit board and connecting it with long traces, you are going straight up. The data path between the processor and the memory is measured in micrometers instead of inches, and the number of parallel connections is vastly greater than what you could achieve with a conventional circuit board layout. This matters enormously for artificial intelligence. The massive AI models that power modern language systems, image generators, and scientific simulations are extraordinarily hungry for data. They need to move huge volumes of information in and out of the processor as quickly as possible. And high-bandwidth memory stacked right next to the processor die on a silicon interposer is what makes that feasible. Without advanced packaging, without through-silicon vias and interposers and chiplets, the AI revolution as we know it could not happen. The transistors provide the computing power, but the packaging provides the data flow, and both are equally essential. Packaging is now so central to chip performance that people in the industry say packaging is the new Moore's law. When you cannot shrink transistors fast enough or cheaply enough, you find gains by being smarter about how you assemble the pieces. The package is no longer just a protective shell. It is an engineered system with its own wiring layers, its own power management, its own thermal challenges. And the thermal challenges are real. A modern high-performance chip can produce 200, 300 watts or more, all generated in an area the size of your thumbnail. Getting that heat out requires metal heat spreaders, carefully chosen thermal interface materials, and increasingly creative cooling solutions. If you cannot remove the heat, the chip throttles itself, and all those billions of transistors might as well be turned off. But even with all this sophistication, with all the layers and the packaging and the testing, there is one more dimension to the chip story that matters enormously. And it is not technical at all, it is geographical. The economics of chip manufacturing are unlike almost any other industry on Earth. The cost structure is dominated by fixed costs that are breathtaking in their scale. A modern leading-edge fabrication plant, what the industry calls a fab, costs $20 to $30 billion to build. That is billion with a B. TSMC's most advanced facilities in Taiwan, Intel's new fabs in Arizona and Ohio, Samsung's plants in South Korea and Texas, these are among the most expensive factories ever constructed by human beings. But once the fab is built and the process is qualified, the marginal cost of making one more wafer is relatively small compared to that enormous upfront investment. Which means the economics of chip making are all about volume. You need to spread that fixed cost across as many chips as possible. The more wafers you run, the cheaper each chip gets. This is why the foundry model, pioneered by TSMC, has been so transformative. Instead of every chip company building its own multi-billion-dollar fab, dozens or hundreds of companies share one fab's capacity. TSMC makes chips for Apple, AMD, Nvidia, Qualcomm, MediaTek, Broadcom, and hundreds of others. That aggregation of demand is what makes the economics work. No single customer could justify the cost of a leading-edge fab on its own, but collectively, they can. And the cost of the mask sets, the stencils used in lithography, tells its own story about how the economics have shifted. At older technology nodes, a complete set of masks might cost a few $100,000. At the 5-nanometer node, a mask set runs $15 to $20 million. At 3 nanometers, even more.
A single mistake in the chip design, a bug that is not caught before the masks are made, means burning tens of millions and months of delay. These enormous costs, combined with the deep specialization required at every stage, have concentrated the industry into a remarkably small number of players. As of the mid-2020s, There are really only 3 companies capable of manufacturing chips at the most advanced technology nodes: TSMC in Taiwan, Samsung in South Korea, and Intel in the United States, with Intel having fallen behind the other 2 and investing heavily to catch up. For the EUV lithography machines that make all of this possible, there is one supplier on the planet: ASML in the Netherlands. For certain critical chemicals and materials, Japan dominates. For chip design software, the United States dominates through 2 companies, Synopsys and Cadence. The supply chain spans the globe. The silicon might originate from a mine in Brazil and be refined in Japan.
The wafers might be cut and polished in South Korea. The photoresist is made in Japan. The lithography machine is from the Netherlands, with mirrors from Germany and light source technology partly developed in the United States. The etching gases come from specialty chemical companies scattered across multiple countries. The finished chips might be packaged in Malaysia or Vietnam, tested in yet another location, and finally placed onto circuit boards assembled in China that end up inside phones designed in California. No single country can produce a modern chip entirely on its own. The supply chain is a web that spans the entire planet, and every node in that web represents deep, specialized expertise that took decades to develop. Pull out any single link and the whole chain breaks. Consider just one seemingly minor component: the photoresist. This is the light-sensitive coating applied to wafers before lithography, the chemical that changes when photons hit it.
For EUV lithography, the photoresist chemistry is extraordinarily specialized. The molecules have to be sensitive enough to respond to the tiny number of EUV photons that actually reach the wafer after 98% of the light has been absorbed by the mirrors, while also being precise enough to produce sharp features at nanometer scales. A handful of Japanese chemical companies dominate this market. If they stopped shipping, the world's most advanced chip factories would run out of resist within weeks. The same kind of dependency exists at dozens of points in the chain. Specialty gases for plasma etching, ultra-pure chemicals for cleaning wafers, precision measurement equipment for quality control. Each one is a potential single point of failure, and each one represents a concentration of knowledge and capability that cannot be quickly replicated elsewhere. And some of those nodes sit in geopolitically sensitive places.
TSMC's most advanced fabs are in Taiwan, an island that China considers part of its territory. The implications of that geographical fact have not been lost on anyone. The United States passed the CHIPS and Science Act in 2022, committing over $50 billion in subsidies to encourage semiconductor manufacturing on American soil. The European Union launched its own European Chips Act. Japan, South Korea, India, everyone is racing to build or attract chip-making capacity. TSMC has agreed to build advanced fabs in Arizona. Samsung is building in Texas. Intel is investing tens of billions in new facilities in Ohio and Arizona. But building a fab in a new location is not just about constructing a building and installing machines. The hard part is the people.
TSMC's fabs in Taiwan benefit from decades of accumulated expertise, a deep pool of engineers and technicians who have spent their careers perfecting these processes, an institutional culture obsessively focused on yield and manufacturing discipline. Replicating that in a new country takes years, even with hundreds of experienced engineers brought over to train the local workforce. Meanwhile, China imports more semiconductors by value than it imports oil. The Chinese government has poured hundreds of billions of dollars into building a domestic semiconductor industry. Chinese companies like SMIC have made progress, but as of the mid-2020s, they remain several generations behind TSMC and Samsung. The United States has imposed increasingly strict export controls to prevent China from accessing the most advanced chip-making equipment, particularly EUV machines from ASML. These restrictions represent some of the most aggressive technology controls between major powers in decades. The logic is straightforward. If you cannot buy the machine, you cannot make the chips. But the restrictions have also created a powerful incentive for China to develop its own equipment domestically. Whether that is achievable is one of the most important open questions in technology and geopolitics alike. Building an EUV machine requires not just one breakthrough, but the integration of thousands of components from hundreds of specialized suppliers, each one representing years or decades of accumulated expertise. The mirrors come from Zeiss in Germany. The laser technology was developed partly by Kymer in San Diego. The precision optics, the contamination control, the vacuum systems, the wafer handling. Each subsystem is its own engineering frontier. Replicating all of that from scratch, even with unlimited funding, would take many years at minimum.
And the moving target makes it even harder. By the time a new entrant masters today's technology, the leading companies will have moved on to the next generation. The moat around advanced chip making is not just money. It is accumulated knowledge, institutional learning, supplier relationships, and manufacturing culture built over decades. And yet, writing off the possibility entirely would be unwise. History has shown that when nations commit enormous resources to a technological goal, surprising things can happen. The question is not whether China can eventually build advanced chips domestically, but how long it will take, and whether the rest of the world's lead will widen or narrow in the meantime. All of this, the concentration of manufacturing, the fragility of the supply chain, the geopolitical maneuvering, is a direct consequence of the physics and economics we have been talking about. The fact that making a chip requires such extreme precision, such specialized equipment, such enormous capital, created this concentration. And the concentration created the vulnerability. The very thing that makes this technology so powerful, the relentless scaling, the incredible specialization, also makes the supply chain fragile in ways that matter to everyone, not just to people who think about semiconductors for a living. National security, economic competitiveness, artificial intelligence, healthcare, energy, all of it flows through chips. And the race to secure chip-making capacity is really a race for sovereignty. A scramble to ensure that if something goes wrong on the other side of the world, a natural disaster, a military conflict, a trade dispute, your country can still build the things it needs to function. Let us take a breath and look at where we are. We started with vacuum tubes, glass bulbs the size of your thumb, glowing hot, burning out every few hundred hours, powering room-filling computers that could do one thing at a time, and were less capable than the cheapest calculator you can buy today. That was the first wall, the limit of what you could build with tubes, and the transistor broke through it. Then we hit the tyranny of numbers, the impossibility of wiring thousands of individual components together by hand without drowning in failures. The integrated circuit broke through that wall, and Noyce's planar process showed how to manufacture them at scale. Then the wavelength of light became the bottleneck, the physical limit on how small we could print. The industry fought that wall for decades. With shorter wavelengths, optical tricks, and ultimately EUV, a machine that required inventing a new kind of light source, a new kind of mirror, and a new kind of mask. Then the transistor itself started failing at small scales, as quantum tunneling turned insulating barriers into leaky faucets. New materials and three-dimensional transistor designs, FinFETs and gate-all-around, broke through that wall. And at every stage, the complexity grew. The number of people who could hold the whole picture in their head shrank. The cost of entry soared. The supply chains stretched thinner and became more fragile. What started as a handful of physicists at Bell Labs tinkering with slabs of germanium has become a global enterprise involving hundreds of thousands of people, trillions of dollars of infrastructure, and the coordinated efforts of dozens of nations. And now we are standing at the next wall. Or rather, we are standing at several walls, converging from different directions. The first is physics. Gate-all-around transistors will carry the industry to 2 nanometers, and perhaps a bit beyond. But the fundamental limits of silicon as a material
are getting close. Researchers are experimenting with exotic alternatives, like carbon nanotubes, channels made of single layers of material just a few atoms thick, and even entirely new computing paradigms that do not rely on classical transistor switching at all. But these are laboratory demonstrations, not production-ready technologies. The second is economics. Each new generation of manufacturing technology costs more than the last, dramatically more. The number of companies that can afford to operate at the leading edge keeps shrinking. In 2001, 23 companies were manufacturing chips at the most advanced process node. Today, that number is 3, and arguably 2.
The cost of developing a new chip at the most advanced nodes can exceed $1 billion, which means only the highest volume products, the processors in the most popular phones and computers, the AI accelerators in the biggest data centers, can justify the investment. The third is energy. As chips get more powerful and data centers grow to support the explosion of artificial intelligence, the electricity demands are becoming staggering. Training a single large AI model can consume as much power as thousands of homes use in a year. The data centers that house these AI systems are being built in clusters so large that they require their own power plants. Some companies are exploring nuclear power specifically to feed their computing infrastructure, and the demand is growing faster than efficiency improvements can compensate. Every new generation of chips is more energy efficient per transistor than the last, but the number of transistors and the intensity of the workloads are growing even faster. The semiconductor industry's march toward more powerful, more efficient chips is now in a race against the energy demands of the applications those chips enable. For the first time in the history of computing, the limiting factor for how much we can compute might not be the silicon, it might be the electricity. And the fourth is geopolitical, which we have already discussed. The concentration of advanced chip making in a few locations, the dependency on a single company for the key lithography tool, the supply chains that span continents and can be disrupted by a natural disaster or a political decision, all of this represents a kind of systemic risk that the world is only beginning to reckon with. Each of these walls is real, each one is imposing, and reasonable people can disagree about which one will prove the hardest to break through, or whether, perhaps, this time the wall really is final. But here is the thing. I have been telling you this story for a while now, and if there is one pattern in it, one thread that runs from Shockley's frustration in the 1940s to the EUV engineers staring at tin plasma in the 2010s, it is this. Every generation thought they were facing the last wall. Every generation had serious, credentialed experts who looked at the physics and the economics and the engineering and said, "This is it. This is as far as we can go." And every generation was wrong. Not because the walls were imaginary, they were real. The physics was real. The constraints were genuine. But human ingenuity, applied by thousands of people working across decades, each one mastering their own small piece of the problem, kept finding paths that nobody had foreseen. Sometimes through brute force, throwing money and engineering hours at a problem until it yielded. Sometimes through elegant sidesteps, like filling the gap between lens and wafer with water to squeeze more resolution from the same laser. Sometimes through sheer stubbornness, like the EUV program spending 30 years and tens of billions of dollars on a technology that many experts said would never work, and refusing to give up even when the doubters seemed to be winning. And sometimes through accidents, like Bratton's razor-slit gold foil pressing down onto a slab of germanium one December day in New Jersey, producing a signal that nobody had predicted and everybody had been hoping for. There is a deeper pattern here that I think is worth naming. The story of the chip is not a story about individual genius, though there were geniuses in it. Shockley was a genius. Bardeen was a genius. Noyce and Kilby and Fagin were people of extraordinary ability.
But the modern chip is not the product of any one mind. It is the product of a civilization. It required physicists who understood quantum mechanics, chemists who could purify materials to 9 nines of purity, optical engineers who could polish mirrors to atomic smoothness, software developers who could write the tools that design the chips, factory technicians who could maintain the machines, business strategists who could organize the economics, and governments that could fund the basic research and coordinate the infrastructure. No single person understands the whole system anymore. The last person who could arguably hold the entire design of a processor in their head was working in the early 1970s, when a chip had a few thousand transistors. Since then, the complexity has outrun every individual mind. Today's chips are designed by teams of hundreds or thousands, using software tools that are themselves enormously complex, running on computers built from previous generations of chips. We use computers to design computers that will design the next computers. The recursive loop would have seemed like science fiction to the pioneers of the 1940s, and yet it works, reliably, at a scale that touches every part of modern life. And right now, somewhere in the world, in a clean room in Taiwan, or a lab in Belgium, or a university in Massachusetts, someone is staring at the current wall and thinking about how to get through it. They probably do not know yet whether their approach will work. They might be wrong. Most of them will be wrong. But if history is any guide, someone, somewhere, will be right. The wall is real. It has always been real. And so far, every single time, we have found a way through. Let me leave you with a thought that brings us back to where we started.
Somewhere in the world, right now, a truck is carrying a load of quartz sand toward a refinery. The sand is unremarkable. It looks like any other sand. If you scooped up a handful, you would not think twice about it. You would let it run through your fingers and brush your hands off on your jeans. But that sand is going to be purified until it is 99.999999% pure. 9 nines of purity. One stray atom in a billion would be too many. The purified silicon will be melted and slowly pulled into a perfect crystal. A single continuous lattice of atoms, arranged with a regularity that borders on the supernatural. That crystal will be sliced into wafers and polished to a flatness that, scaled up, would make the Great Plains look rough. Those wafers will be coated, exposed, etched, implanted, deposited upon, and polished hundreds of times by machines so precise that their alignment tolerances are measured in fractions of a nanometer.
The whole process will take months and cost millions. And at the end, from that truck full of dirt will emerge chips containing billions of transistors, chips that can recognize faces, translate languages, navigate cars, predict weather, and carry every conversation, every photograph, every piece of music and video you have ever cared about in something that fits in your pocket. Sand into thought, dirt into dreams. The entire arc of this story, from Lee De Forest's vacuum tube in 1907 to the EUV machines of the 2020s, spans just over a century. 100 years to go from a glowing filament in a glass bulb to a machine that creates miniature stars to print patterns smaller than a virus onto crystallized sand. 100 years in which the fundamental question never changed. How do you control electricity? How do you make it switch, amplify, compute? The answers kept changing. The scale kept shrinking. The complexity kept growing. But the question at the heart of it all remained the same one that Shockley and Bardeen and Brattain were wrestling with in that lab in New Jersey in 1947. And the walls kept coming. Every decade brought a new one. Every generation of engineers looked at the wall in front of them and said, either out loud or privately, there has to be a way through this. And so far, there always has been. If that is not worth lying here thinking about for a while, I do not know what is. And somewhere, in some clean room, under lights that never turn off, someone is working the night shift. The clean room never sleeps. Fabrication is a continuous process, 24 hours a day, 7 days a week, 365 days a year. The wafers move through the tools on automated tracks, cycling between chambers, being heated and cooled and etched and coated over and over for weeks on end.
And the people who tend these machines work in shifts, wearing full-body suits that make them look like astronauts, breathing filtered air, touching nothing with bare hands. Right now, one of those people is staring into an electron microscope, checking whether the latest adjustment to an etch recipe improved the yield by 0.1%. Somewhere else, a designer is running one more simulation on a cluster of servers, trying to close timing on a circuit block that is a few picoseconds too slow, and knowing that if the timing does not close, the chip will not hit its target frequency, and months of work will need to be revisited. Somewhere else, a scientist is experimenting with a two-dimensional material, a sheet of atoms just a single layer thick, wondering if it might have the electrical properties needed to carry the industry past the limits of silicon, 5 or 10 or 20 years from now.
Somewhere else, an engineer at ASML is working on the next version of the EUV machine, the high-NA version, with a larger numerical aperture that will push resolution even finer. The mirrors need to be even more precise. The light source needs to be even brighter. The contamination controls need to be even tighter. Every problem solved reveals the next one waiting, as it always has. And somewhere else, in a boardroom or a government office, someone is looking at a map and thinking about where the next fab should be built, how to secure the supply of critical materials, how to train the thousands of engineers and technicians who will be needed to run a factory that costs more than a sports stadium and takes years to bring online. They are all part of the same story, the same long, improbable, beautiful story of people figuring out how to take the most ordinary material on Earth and arrange its atoms in just the right way to make it think.
That story started in a lab in New Jersey, with 3 men who could barely stand each other, pressing gold foil onto a piece of germanium and watching a signal appear on a screen. It continued in a quiet office in Dallas, where a lonely engineer sketched a circuit on a single chip during a 2-week vacation nobody else was taking. It continued in a garage in Palo Alto, in a clean room in Phoenix, in a conference room in Feldhoven, in a factory in Hsinchu. It continues right now, one layer at a time, one wall at a time. And if you are still awake, lying there in the dark, here is one last thought to carry with you. The phone on your nightstand, that little rectangle of glass and metal, contains a chip with more transistors than the number of seconds that have passed since the pyramids were built. Every one of those transistors was printed using light from a plasma that burns hotter than the surface of the sun. The silicon came from sand. The copper came from ore. The knowledge came from centuries of science. The walls are still coming. They will always be coming. And so far, so will we.